Well, hello, everyone. My name is Russ Tubner.
And I'm Greg Smith.
And together we're going to be talking about a topic that we call finding and fixing inefficient mainframe integrations. Thank you very much for taking your time to join us today. We look forward to sharing a lot of information with you and then hopefully having some really good Q&A at the end. So again, thank you very much. Our first slide is all the obligatory disclaimers. Certainly won't belabor this, but we'll move on from here. This is our agenda for today. We're going to be with a lot of content. We're going to move very quickly. At any point along the way, if you have a question, please feel free to jot it down. We look forward to either answering them at the end of this presentation in the breakout session, or subsequently, we'd love to hear from you directly after this presentation. Our speaker bios are present in the deck. We won't belabor these points. Suffice it to say that Greg and I have been working on the development of this technology for a number of years. While we come from very different backgrounds, we've been able to bring our various skill sets, Greg's in data analytics and mine on the mainframe, to be able to create a technology platform that allows customers to be able to find and fix inefficient sources of integration. So let's first of all ask a very simple question. Why? Why integration analytics? And for that matter, what does it even mean? Well, we have a perspective, we have a view, and I hold this view having been involved in the mainframe industry for many decades, and that is that inefficient integrations are a significant barrier to modernization. No doubt this chart represents your environment as well, where you have lots of endpoints on outside of your network, hundreds, thousands, tens of thousands, maybe hundreds of thousands of endpoints interacting across various networks and various channels of communication into System Z. And how that is engineered and how those integrations occur are very, very important. Because inefficient integrations have a number of detrimental effects. They can inject latency, they can degrade quality of service, they can add transactional load even. They can waste MIPS, compromise ROI, and the bottom line is make it extremely difficult to modernize System Z applications. Now, we also have a very strong view here, and it's really the underlying premise of the entire integration analytics effort. And that is that you really can't fix what you can't see. Now, to resolve that and to be able to let you visualize and see what's really going on in your integrations, we developed HTAC. HTAC is a diagnostic platform designed to help you find and analyze inefficient patterns of CICS integrations. And that's what we refer to by this phrase of integration analytics. Our objectives are both simple, but they are very detailed. That is, we want to not only find common and wasteful patterns of integration, but we want to quantify the impact. Furthermore, we want to reveal the business purpose of those integrations. And what we mean by that is showing the DNA, what's really happening through an integration process or sequence. And then we want to provide customers with actionable intelligence about how they can find and then fix problematic integrations. Let's talk a little bit more about the need. Again, let's come back to this reference diagram and just observe that most organizations have really good tools to analyze the activity in each one of those silos, the silos being denoted by the brackets. So many customers have great tools for finding out and exploring what's going on the exterior side of their network. And they have good tools for being able to understand and gain insight about what goes on the inside, the interior side of their network. And then they have good tools to be able to see what's going on under the covers of the mainframe. But the key observation we want to make here is one that is very, very important. And that is that optimizing each of these silos does not ensure that the overall integration is efficient. Now, that's in fact what we're trying to do with our focus on integration analytics. We want you to be able to see the forest for the trees. We want you to be able to gain a view of your network that transcends those individual silos. We want you to be able to track transaction activity back to the origin. We want you to be able to assess the business purpose and value for various patterns of interaction and integration, all for the purpose of letting you analyze and assess both the performance and the cost. Now, in order to fulfill that objective, we created a framework. And I will put the components of the framework up here. Time does not permit us to really go into a lot of detail on each of these, but let me just hit the highlights. First of all, a key part of our framework is the deployment of some CICS exit code that allows us to gather little bits of metadata about each and every targeted request. Now, in some cases, these exits are not required. In fact, when we do a POC, our first cut usually is we don't ask anyone to install these. But those exits are key to being able to really gain deep and rich insight as to what's really going on with all the interactions between the outside world and your mainframe. We'll see an example of that in a minute. But we refer to that process of gathering the metadata and then enriching the SMF-110 data as, generally speaking, enrichment. Then once we have enriched the SMF-110 data, we then transport it down to a proper analytics platform, which currently we use Splunk. From there, we use that platform to do various kinds of pretty sophisticated analytics with some light AI and ML thrown in to help you really see what is driving your mainframe load. Let me move into a bit of an overview of a component that we call the macro hunter. Now, up to this point in time, what I've described about the HTAC framework is that it really is a generic platform that we intend to be applied to many different problems associated with integration. However, as we began working with customers over the last few years, we began to see one style of inefficient integration over and over, and it was this: client, server, or cloud-based programs or tools, and that is running off the mainframe, but they were automating the execution of screen-oriented mainframe applications. It may be 2022, but terminal emulation and screen scraping is alive and well. And there are many factors in the industry right now, such as the deployment or the growing deployment of RPA platforms that are actually driving this pattern of integration further. We built the macro hunter component for you to be able to see this, assess its impact, and then remediate it as appropriate. Now, to be sure, there are some use cases of doing emulation and screen scraping that are simply harmless. But as you'll see in some of our demonstrations, some are very harmful and very wasteful of your System Z assets. Now, I won't go into this slide in too much detail, but let's just remember together why this approach is problematic. So let's imagine we have all of this collection of devices and endpoints on the left side of this diagram. And let's imagine that they are interacting step by step, screen by screen, keystroke or enter key by enter key with a transaction running under the covers of CICS. Well, what you end up with is a pattern of integration that has at least three very problematic attributes. First, it's a pattern of integration that generates a tremendous amount of latency because each request and response requires a full travel across the network. Secondly, it has a lot of overhead. In most organizations, when such a request comes in to the mainframe, it's going to go through a TN3270 server, which then goes to VTAM, then probably through a session manager, then back out to VTAM again, then on into CICS, finally actually running the transaction. And when the transaction actually runs, it might take 100 microseconds then the output transits all the way back. In essence, in many cases, organizations are spending let's say round numbers, 100 milliseconds full travel, if not 200 or 300 in some cases, in order to execute a transaction that is taking microseconds. That's the problem. Now, as we begin to discuss both HTAC and the macro hunter component, let's go ahead and define some terms and concepts. First of all, I've already used terms like RPA or bot, script, or macro, and we use these interchangeably to simply describe something, a program or a tool that's automating the execution of these screen-oriented transactions. We don't really care about the source of the automation. It could be an Excel macro, a VBA script, a UiPath bot, or a custom program. Analytically, they all look the same. We also use the term DNA. DNA to us describes the sequence of steps that the macro or bot perform. Now, as you might imagine, DNA sequences can be very long, especially if a bot or a macro is automating a sequence of 1,000 or 10,000 or 100,000 steps. So in order to be able to compress that down into a more manageable analytical form, we create what we call a signature. And a signature is nothing more than the DNA of a macro or an RPA that's expressed as an MD5 hash value. And you can see an example there. Many times, just for convenience, we will refer to a signature by its first 4 characters. So you'll see that in a couple of slides. But you never really have to worry too much about the complexity of the signature, because every time you see such a signature, you can always click on it and go see the DNA in an actual dashboard. Bottom line, for each DNA sequence, a unique signature or identifier is generated, and that unique identifier is really important because it allows us to hunt for the most common and problematic use cases in an organization. Now, the second step of background or grounding I would like to provide is to just give you an idea of some of the analytics that we keep track of and that you'll see as we look at some other slides and or a live demo. So it is in most cases, when you're looking through these dashboards, you're going to see an analytics screen, something like this. Now, I'm going to walk through each of these values so you can get an idea of what they mean. First of all, I always look at RPA total, and that is the total number of transactions that were executed as part of the RPA. Now, again, I could have called this macro total or bot total. Again, don't get hung up on the 3 letters RPA. It's just a placeholder to indicate that source of automation outside the mainframe. But what we're showing here is an RPA that when it fired up, it ran 10,503 transactions in rapid succession. RPA duration is the length of time from the beginning of the first transaction to the end of the last transaction. So that is the duration of this work process from the vantage point of the component, of the bot, of the macro outside the mainframe. It thinks this process took 22 minutes and 30 seconds. Now, the next column, RPA-TX duration, that highlights how long the actual transactions really took. Well, in this case, the transactions really took 1 minute and 33 seconds under the covers of CICS. That's it. Now, that always begs the question, well, what happened to the other 21 minutes? Well, it never fails that those other 21 minutes, or whatever that discrepancy is, that amount of time falls into 2 buckets. First is latency. We talked about this pattern, this form of integration requires multiple hundreds, in this case, 10,000 round trips across a global corporate network. That takes time. The other component of the difference between RPA duration and RPA-TX duration is any time required by the automation source, the bot or the macro, to do its automation thing. We computed what we call a duration ratio just to highlight this disparity and help draw your attention to the most egregious cases. Of course, we also want you to be able to see the RPA CPU time, that is the total CPU time consumed by those 10,503 transactions. We also calculate a rate, a transaction per second rate. In this case, it was 7.8. If we were to do this with your data on your system, you may find them lower, but you may find them drastically higher. The RPA statistics is simply a column that shows that for each transaction that was part of the sequence, how many times was it executed? Well, in this case, it's very simple because it only involved one transaction called ORR, and it was executed 10,503 times. Now, we finally end up at the DNA column, and this is a very simple example, and you're going to see some in the next slide that are much more complex. But let me tell you or decode this very simple case. What this is telling me is that what this macro or bot did was it ran the ORR transaction by pressing the enter key. So that ORR plus enter says enter was the AID key. And the star then followed by a number indicates the number of times that that DNA occurred or that action occurred back to back. So in this case, a bot executed the ORR transaction, pressing the enter key 10,503 times in rapid succession back to back. Now, we form the DNA the way we do in order for a subject matter expert to look at that and perhaps have an aha moment or wonder, why are they doing that? When we showed this to the application SME, they very quickly surmised what was going on, and that is that the ORR transaction, on that screen, it shows the status of a pending order. And what this macro was doing was essentially pressing the enter key every 200 milliseconds in order to detect a status change of the order. For example, going from pending to fulfilled. Now, I think we can all agree that there must be a better way to architect status change notification, given that that's an important business function. There's got to be a better way to architect this than taking 22 minutes and running 10,000 transactions. But these are the sorts of insights that organizations simply can't see a lot of times. Right? And again, it goes back to our point, which is you really can't fix what you can't see. And so we're trying to bubble this up. We're trying to surface this data so that then you can see what's really going on and where remediation is required. Now, I'll put this up just for a little bit, just to show you a more complicated example of DNA. But again, I just want to reinforce that it's the DNA, that's the treasure we're really hunting for. In this case, it's a much more sophisticated business process, and I won't certainly belabor all of it or explain all of it, but that one highlighted section there, I will just decode that for you just so you can get an idea. What that is telling me is that the PBSE transaction ran in an AOR called CIA4. It was run as a result of pressing the enter key, or the bot stating that the enter key had been pressed. Then the greater than sign indicates something about the output of that transaction. The CM10M03 dot, and then the same value, that is the map set and map name of the BMS map that was sent in response to that transaction. And then in parentheses, CM10P003 is the name of the program that did the BMS and map. The *2, of course, now indicates that this was done back-to-back or 2 times in a row. Now, the level of DNA or the detail in the DNA can vary based upon your environment, your preferences, or your needs. In this case, the organization wanted to be able to see DNA down at this level, so the product can certainly show it. At this point, I'd like to pass the microphone over to Greg, who will give you a little bit of a view behind the scenes of HTAC and Macro Hunter and walk you through some sample dashboards, all leading up to a live demo. Greg.
Thank you, Russ. Hi, I'm Greg Smith. I'm one of the developers of the Macro Hunter. If we can go to the next page. This is a high-level architecture and data flow diagram that shows that the analytics piece of the HTAC product is implemented in Splunk. It's a multi-stage process. We've developed a very robust but scalable product because some of the data sets coming from the mainframe are humongous. And so we had to determine how to do that. The only piece of this that's really interacts with the customer, though, is the dashboard on the far right. And I want to just really introduce that to you in the next few slides. Next. Different clients have different needs, and this time domain set of visualizations allows a user to correlate between operational issues and RPAs that are occurring on their system. And so you go from the day that you want to deal with, that your existing monitoring tools where you've isolated a particular day, a particular time that some issue is occurring, and then you come to Macro Hunter, and then you can isolate what is occurring during that frame. So you go from hour, from day to hour, down to minute level, and then you can actually choose a minute to determine what's occurring during that time frame. Next. This is one of the most important visualizations for your dashboard, and we call it the bubble charts, and it's actually pivotal in that it tells you three attributes of the who, where, and what relating to the macros. And so, on each of these charts, it gives a total of 10 RPAs that gives you the total CPU time, which deals with cost, and your total duration, which deals with quality of service. And just for example, over just the next few slides, I want to use two of the macros, the AF66 and the 614E macros, or RPAs, to highlight how to use our Pareto charts, which are just sorted bar charts. So Russ, if you could go to the next slide. So let me show you how to read these Pareto charts. There's a maximum of 10 RPAs that encompass each of these Pareto charts. Even though there's only 10, if you look at the title of the chart, it shows that 3,160 are not shown. So if you notice in the thin line that's within the bar chart, these 10 RPAs encompass 30% of all the RPA executions that were executed within the time frame and selections you've chosen through the menu. So this is pretty significant. But you'll notice that the 614E macro, which was the largest bubble on the bubble chart, actually accounts for 12% of all the RPA executions. So this is pretty significant. And the other significance to these Pareto charts and the bubble charts is to highlight the point that even though you may have thousands or tens of thousands of RPAs running on your system, to have significant gains, improvements on your performance of your mainframe, you really don't have to boil the ocean. This narrows down very rapidly. In fact, once you learn to read these charts, in a matter of a couple of minutes, you've already isolated just a few RPAs that you need to go mitigate. Russ, next chart, please. So this particular chart deals with the CPU time. And so you can see that the AF66 particular macro accounted for 9% of all the CPU time associated with the window that you've selected. And these 10 RPAs account for 42% of all the execution time associated with the RPAs. And so again, to reiterate, you don't have to boil the ocean to solve a significant part of your performance issues. So I believe that's the last slide in my area. So Russ, I'm going to turn to you for a live demo.
Okay, Greg, thank you very much. We will do a live demo now. So let's go ahead and get set up for that. What I'm going to be showing you on your screen right now is a browser, and we are live using one of our Splunk instances. I'm going to go ahead and refresh the screen just to get all the data up and running. And we're going to move through this quickly, but I just want to illustrate what Greg was showing you on some of the slides. And that is that this is a small set of data going back from March of 21. And we just have a limited bit of time. But as Greg illustrated, I can click on that bar chart, and then I can see the hours for which I have data, and I can see the level of RPA or bot activity against the CICS environment. So let's just click on the highest bar chart, click on that, and then I can break it down to the minute level. Now, this is a feature, as Greg indicated, that was driven by our customers, because we have a number of customers who are really worried about about RPAs, macros, and bots really causing complications operationally in their environment. So they want to be able to drill down to the minute level. So if I click on that one bar chart, I can go over here and I can see exactly what was going on in that minute. Now, this is a low volume customer, but even then, we detected 31 bots were running within that minute. And then we can show you the exact DNA of what they were doing. Let's go back over to the bubble charts, because to Greg's point, it is really important to realize that when it comes to finding and fixing these sorts of inefficient sources of automation, you don't have to boil the ocean. You just need to find the most egregious cases. Now, in just looking at this chart, this bubble chart, I still remember the day we looked at it the first time. What does this tell me? This tells me that there are 2 IP addresses that represent the bulk or are causing the bulk of the macro or RPA activity. There's something at an IP address ending in .79 and .78. So we picked up the phone and we called the customer and said, hey, what's at .78 and .79? And the answer came back, well, those are 2 very large servers running a product from IBM called HATS, Host Application Transformation Server. We said, that's really interesting, because they are driving the vast majority of all macro and bot activity. We went over here to this chart, this bubble chart, and had another aha moment, and that is, wow, there is really only one signature, one macro or bot that is responsible for the bulk of all CPU time consumption and all latency or real-time delay. So let's just click on it. Let's see what it is. And we can go over here and we can now take a look at the DNA. Well, there it is. Now we're going to look at this a little bit more in a minute, but that is the DNA of this one activity. Now, we formulate this DNA using our own proprietary approach, which allows us to look for similar patterns that are occurring. So as a result, here is that DNA being used, and it encompasses 18 transactions. I will sort it in descending order by number of transactions executed, and you can see that it also, that same DNA is executed in certain cases up to 105 transactions. Let's now take a look at this DNA, because this is an excellent case where sometimes it takes an experienced human to really detect and understand a bad bot. So here is our most common DNA. And with that, I'm now going to cut and paste that and put it in to a PowerPoint slide, and we're going to take a look at it. So let's go back into presentation mode, and let's do what we call a little bad bot analysis. There it is. There's the bot that is consuming the bulk of all of the CPU time that bots are consuming, and it's also responsible for the highest amount of latency or imposed delay, end user delay. Now, if you are a CICS person and you look at that DNA, the first thing you're likely to observe is this, or ask as a question: I wonder why the clear key is used so frequently. And for that matter, why is it being used back to back? That seems really odd, since in most applications, a clear key is intended to get the application back to a clear screen or a neutral state. That seemed really odd. Well, what we did is we called the customer. And we said, this is really interesting. Okay, you've told us that these macros, that these bots are being run from the IBM HATS platform, but what's really going on here? And they explained that that sequence was really not implemented by one single macro, but sort of like a main macro, which invoked 5 smaller subroutine macros. And so knowing that, we then broke them out a little differently, as we did on the right side of the screen. Now, this is where it gets interesting. This macro was written by some very talented, well-meaning developers who understand HATS really well. But they didn't necessarily understand CICS, nor did they understand the application. So what they did is they wrote each of those subroutine macros to be a good citizen or a good macro. And then they also decided that they would defend themselves against bad macros or bad citizens. So as a result, the first thing they did in each macro was clear the screen, putting the CICS app in a known state. And they would do whatever they need to do, maybe only run one transaction. And then at the end, they would clear the screen again to leave the session in a known state. And again, they would do this even if the macro only ran a single transaction. Now, I think everyone who can already start to intuit what the problem here is. But when we showed this to the subject matter expert, they had their aha moment and said, oh no, that clear key is not even required. It is never required to exit the application completely in order to run another leg. And that's because there was a field in the upper left-hand corner where someone could directly enter or type, so to speak, the name of the next function to be executed. So all in all, when we looked at this, we decided it's just a amazing use case to highlight the unintended consequences of macros and bots, particularly written by people who don't understand either the subsystem like CICS or the application and how it was really written or meant to be navigated. Well, in this situation, once we did all the math, it became very clear that 50%, and I mean that 50% of all transactions driven by HATS to CICS had absolutely no functional or business values. These macros or these transactions, these steps were an absolute waste of mainframe CPU time and contributed significantly to degrading end user response time. I don't think there's any doubt about the fact that this would stand as an example of a bad bot. And that's really what you're trying to spot in this sort of analysis. You need to be able to find the bots that are the most egregious in terms of either inefficiency and causing your end users to become less productive, or are simply wasting mainframe CPU time. Now, we have honed in on a very particular use case, and that is what we call, with our macro hunter component, where we're looking for patterns of terminal emulation and screen scraping that become really inefficient and expensive. But there are many other patterns of integration, and HTAC as a platform is meant to be able to help you address those as well. We've listed some of the other cases that we're working on. We're also focusing right now internally on some use cases in and around ZOS Connect to meet the needs of some of our customers. ZOS Connect is a wonderful product, but the thing to remember is that it creates an API around a single CICS program. As a result, if your business process requires the execution of multiple programs, then multiple APIs must be designed, developed, and invoked in order to perform that process. And all of that orchestration, which is usually done outside the mainframe, it again drives and reinforces very costly and inefficient patterns of integrations. We're going to move now into our Q&A time. So let me close by simply saying we look forward to your questions, and we also look forward to hearing from you about what your challenges may be when it comes to difficult or potentially inefficient patterns of integration.